Welcome to Lecture 2 of Module 9. In this lecture, we're going to be talking about cyclotron resonance. This is the mathematical treatment of what we covered in Module 2 on nuclear magnetic resonance and magnetic resonance imaging. It's also an example of an exact solution of time evolution, and there are very few exact solutions of time evolution that we have. So we're going to be looking at what's called cyclotron resonance. It might be useful for you to go back and review the NMR lecture from Module 2, where we examined spins precessing in a large magnetic field. We then turned on a rotating perpendicular magnetic field that rotated at precisely the same rate as the rate of precession. What we're showing for you here on the bottom, on the left-hand side, is just a schematic of what the effective arrow that represents the current loop is. In the next plot, we're showing what precession looks like for the motion of that current loop in the large static magnetic field. Then the next image is showing the rotating frame where this rotating magnetic field that we're putting in is stationary because we're rotating at exactly the same rate as the rate of precession. And in that frame, you can see that we then precess about that yellow direction of that second magnetic field, and you can see that the projection goes from up to down, back to up, and so forth, and it keeps flopping back and forth, and that's called Rabi precession. Then in the last one, we're showing what this looks like in the lab frame, and you can see that the effective needle that represents the current loop, or that represents the spin, is going through what looks like a rather erratic motion, but it really is just doing this Rabi flopping up and down, but now in the lab frame as opposed to in the rotating frame. Now, in the frame of the precessing spin, as we just mentioned, it sees the second field that points always in the same direction, so it's going to precess around that field. And then this causes the spin to flip from up to down and back again. And again, that's what we call Rabi flopping. All right, so let's now get mathematical. Let's talk about the Hamiltonian of a spin in a field. So recall that in a field, the spin acts like a magnetic dipole. So the Hamiltonian is just minus mu dot B. Mu is given by minus GE over 2mc times the spin operator dotted into the magnetic field. We make that collection of constants that multiplies the spin. We call that gamma. And if I assume that the magnetic field is pointing in the z direction and has a magnitude b0, it'll be gamma b0 times sz divided by h bar. And we give that combination gamma b over h bar a name, or sorry, gamma b0, because there's a h bar in the sz. We give that combination gamma b0 a name. We call it capital omega, and that's the Larmor frequency. So the little gamma is called the gyromagnetic ratio. It's GEh bar over 2mc. Omega is gamma b0 over h bar. That's called the Larmor frequency. And as I had mentioned before, we chose this magnetic field to lie along the z direction. The eigenstates of the Hamiltonian, the Hamiltonian is essentially just proportional to sz. So there are friendly states, the states of definite angular momentum. I can also classify them according to the total angular momentum, and these states we label by S and M, but frankly, I only need the M label for these states because that's what will govern the energies of the eigenstates. And the energy eigenvalues are just given by minus big omega times little m. So minus h bar times the Larmor frequency times the magnetic quantum number m. Now, the time dependence of a state, of this eigenstate, is very easy because the Hamiltonian is time independent. So we let e to the minus I over h bar, h hat 0 times t, act on the state. Because the state is an eigenfunction of m, and the eigenvalue under h hat is minus h bar omega. I see there's a small typo there. It's going to have a time evolution given by e to the plus I big omega mt. Acting on the state. So it's going to have a phase there. And I'm sorry, there's a small typo there. This is what we call precession of the spin about the axis of the field. So that whole notion of precession of the spin, you can think of as just this phase that multiplies the eigenstate. Now let's talk about the magnetic resonance experiment. We're going to add in a small perpendicular magnetic field that rotates about the z-axis. When that rotation frequency matches the precession of the spin, the rate of precession of the spin, then we're on resonance. And in this case, the spin sees a second field in one direction in the xy plane, so it's going to precess around that field. That's going to cause it to flip from up to down, and that's a process that we call the Rabi oscillation. We're now going to get very mathematical and describe in detail exactly how this works using our operator formalism. So the magnetic field has two pieces. It has the large magnetic field in the z direction, so B0 is much bigger than B1. And then it has this rotating magnetic field in the xy plane. We have the magnitude B1, and the rate, the angular frequency that it rotates at is omega. So we'll have a cosine omega t Ex minus a sine omega t Ey for that rotating magnetic field in the xy plane. The Hamiltonian is minus mu dot b, so you get minus omega times sz minus gamma b1 over h bar, sx cosine omega t minus sy sine omega t. Now, our next step is going to go to what's called the rotating frame, which rotates at the same rate as the rotating magnetic field. Actually, we're going to do the transition for an arbitrary frequency for the magnetic field. We'll always be going into the frame where the magnetic field is pointing in a constant direction. Now, back in Module 7, we learned that rotations are generated by angular momentum. And so the operator that will transform to the rotating frame is simply one of these rotation operators. We're going to call it d hat of omega t comma ez. The omega t is telling me the total angle that we're rotating by, and the axis of the rotation is that vector ez. So this operator is going to be e to the minus I over h bar omega t times the operator sz, because this is the generator of a rotation about the z-axis. Now, the spin transforms according to S alpha of t is d dagger omega t ez, S alpha d omega t ez. And we're going to just plug in for what these are. Let's take a look at the z direction. Because sz commutes with itself, I can just move that Hadamard through the sz, and it's just sz. There's no time dependence. Of course, if I have an object that's along an axis and I rotate about that axis, I don't change the object. Now for Sx, we work this commutator out by using the Hadamard identity, or we work this expression out by working on the Hadamard identity. So we get an Sx cosine omega t minus an Sy sine omega t, and then a similar thing for the y. It goes to Sx sine omega t plus Sy cosine omega t. And these then are our three transformations. The Sz is left alone, and the Sx and the Sy, they're rotating. Now, even though previously we calculated this by explicitly evaluating the Hadamard, I'd like to also show you how you can do this via a different method, which is called the equation of motion method, or the differential equation method. So we're going to call this object, this operator object, we're going to just call it fx of t, and then we're going to take the derivative of it. And when I take the derivative, I'm going to pull out a factor of I omega over h bar. Then I'm going to have an sz to the right of the sx minus an sz to the left of the sx. But that's just the commutator of sz with sx. We can evaluate that commutator. It's going to be an ih bar. Because zxy is in cyclic order, it's going to be an ih bar sy. And then the ih bars will cancel. I'll get a minus omega. And then, of course, this combination, e to the I over h bar omega t sz sy, e to the minus I over h bar omega t sz. That's a new function. We're going to call that fy of t. So fy of t is this Hadamard of the sz. We take its derivative, and in this case, we pull down that I omega over h bar, and we evaluate that commutator. The h bars cancel. I times minus I gives me a plus 1. And we find that it is equal to omega times fx. So we have these two equations. Fx dot is equal to minus omega fy, and fy dot equals omega fx of t. If I take a second derivative of that first equation, I'll get f double dot x of t is minus omega fy dot of t, but fy dot of t is omega fx of t. So I'll get that fx double dot of t is equal to minus omega squared times fx of t. Now that's a differential equation we know how to solve. I'll pause for 5 seconds for you to remember what the solution is. I hope you said that it is sines and cosines, because indeed that's what it is. If we set omega t equals 0, we see that the coefficient of the cosine is what fx is at time t equals 0. And similarly, if we take a derivative and then look at what happens when t equals 0, we find that the coefficient of the sine omega t over omega term is fx dot of 0. But we know what these are. Fx of 0 is just equal to sx, and fx dot of 0 is just equal to minus omega sy, so we can plug those in. And you see that this is the same answer as what we wrote down before by looking at the Hadamard of this, which of course has to be the case. It has to give the same answer. Now I can do the same thing with the fy, and when I do it with the fy, I'm also going to get a similar equation. But it turns out that it's the fx that we care about because it's the fx that appears in the h of t. So that combination, sx cosine omega t minus sy sine omega t, that is just given by e to the I omega t sz sx e to the minus I omega t sz. And you can see I can also do that Hadamard around the sz, and it gives the same thing. So I'm going to also now put a Hadamard around the sz. So I get it around both terms in the Hamiltonian. And now you see I've done a factorization. And look inside that parenthesis. You see, by going to this rotating frame, we've removed all the time dependence from the Hamiltonian. So the Hamiltonian can be re-expressed as the rotation of a time-independent Hamiltonian. Now this is great because time-independent Hamiltonians we know how to do time evolution for. This is a unitary transformation that takes us from the static frame to the rotating frame. And that means I can do a unitary transformation on the states. And so that's what we're going to look at next. So remember, the Hamiltonian is written as this unitary transformation. You can think of that as a U dagger, static Hamiltonian times a U, as a sandwich, if you like. And the idea is that we're going to define a rotating wave frame wave function via psi rotating as e to the minus I omega t sz times my original wave function. Or if I take my rotating wave function and multiply it by e to the I omega t sz, I'll get psi of t. Okay, then let's look at our equation of motion, or our time-dependent Schrodinger equation. It says IH bar d by dt psi of t is equal to h of t psi of t. So let's plug in what h of t is in this factorized form using this unitary operator. And it's acting on that state psi of t. Now, you can recognize that e to the minus I omega t sz psi of t, that is just psi rotating. So I can replace that by psi rotating. And now what we're going to do is we're going to multiply by e to the minus I omega t sz from the left on both terms. And then what I'm going to do is I'm going to multiply by 1, multiply by e to the plus I omega t e to the minus I omega t. E to the minus I omega t times psi of t is just equal to psi rotation. So I can replace that derivative by e to the I omega t sz psi rotating frame of t. Now I can take the derivative. There are two terms. One where it hits the exponential. That's going to pull down a factor of I omega times sz. And then once where it's going to act on the operator. The I omega times sz is going to give me a minus h bar omega times sz. And then those exponential terms are going to cancel because I have an e to the minus I omega t and an e to the plus I omega t. And the term with the derivative, those exponential terms are going to cancel as well. So those exponential terms are going to go away. I have this extra term, minus h bar omega sz psi rotation. I'm going to bring that to the right-hand side. It's going to be subtracted from the big omega. And we get this nice Hamiltonian equation. And the thing in the parenthesis I can think of as the effect of Hamiltonian in the rotating frame. And you can see that that is a time-independent object. But a time-independent problem is easy to solve for the time evolution. It's just e to the minus I Hamiltonian times time divided by h bar. So I can just calculate that exponential directly and have it act on our initial state. Our initial state, because I'm working in the rotating frame, is psi of 0 in the rotating frame. But because psi in the rotating frame is related to psi in the lab frame by an e to the I omega t as z, when t is equal to 0, that number is 1. So that's also equal to psi in the lab frame. We're now going to multiply by e to the I omega t as z from the left-hand side. We're going to do that on both terms. And we're going to now replace that psi rotation by psi in the lab frame, e to the I omega t as z. That is psi in the lab frame. So I'm going to get psi in the lab frame is e to the I omega t as z, I over h bar, big omega minus little omega t as z plus I gamma b1 t over h bar squared sx, all acting on the initial psi of 0 in the lab frame. Now look at this. It's pretty neat. We've taken something that should nominally be a time-ordered product, and we have factorized it into the evolution operator of two time-independent Hamiltonians. That's pretty neat that we've been able to solve the problem in this fashion. This is one of the few time-dependent problems that can be exactly solved. All right, what is an application of this? Let's take a look at what we can do with this. Time-dependent quantum mechanics problems are almost always about transitions from one state to another. So the idea is we start in a definite state. Oftentimes we start in an eigenstate of the H0. In this case, that's what we're doing. Definite state Sm, and we ask what is the probability to be in the state Sm prime at time t. So that probability is just equal to the overlap of the state Sm prime and the state psi at time t, which we can get from the state at time 0 by applying the evolution operator to that state. And then I have to take the modulus squared of that. Again, remember, multiplying by the bra asks how much of that state that is represented by the bra is in the state that I'm taking the inner product with on the right-hand side. Of course, because we need a probability, we have to take the modulus squared of this. Now, e to the I omega t as z, that's going to act on the state I'm going to get in e to the I omega m prime times t. And that's, of course, just a phase. So when I take the modulus squared of that, I'm going to just get 1, so we can get rid of that term. And now this is the expression that we have. That's the general expression. To see how it works in practice, let's take a look at a spin 1/2 example. I want you just to remember how we represented spin for spin 1/2. Sz was h bar over 2 times the sigma z Pauli matrix. Sx is h bar over 2 times the sigma x Pauli matrix. And then we had this really neat identity that we had derived, e to the I v dot sigma, where v is a vector of numbers and sigma is a vector of Pauli matrices. That's equal to cosine v times the identity matrix, which I explicitly suppressed the identity matrix here, plus I sine modulus of v times v dot sigma over modulus of v. Now, in our case, v, I can read it off from that exponential. It's gamma b1 t over h bar, 0, omega, big omega minus little omega t. And then I can calculate the modulus of v. I'm going to get a t over 2 square root of gamma squared b1 squared over h bar squared plus big omega minus little omega squared. And we're going to define delta to be that square root, so we're going to call that t delta divided by 2. All right, let's work out what that probability is. The probability to flip means that I start in the state plus 1/2, and I ask what is the probability that I end up in the state minus 1/2. We plug in what that exponential is. It's a cosine t delta over 2 times the identity matrix plus I sine t delta over 2 gamma b1 over h bar delta sigma x plus big omega minus little omega over delta sigma z. I take this sandwich between the state with the 1/2 minus 1/2 and the initial state on the right, the 1/2, 1/2. All right, now, this is the off-diagonal matrix element. The identity has no off-diagonal matrix element, so that term contributes nothing. The sigma x has a 1 in that off-diagonal matrix element, so I'm going to get an I sine t delta over 2 gamma b1 over h bar delta, and then sigma z is diagonal, so that gives no contributions. I have to take the modulus squared of that, so we get the probability to flip is sine squared t delta over 2 gamma b1 over h bar delta quantity squared. It's probably comforting to you, it certainly is to me, that as t approaches 0, the probability to flip is 0. I have to have the Hamiltonian on for some period of time, before the spin has any chance of flipping. All right, let's calculate the next matrix element. That's P 1/2, 1/2. I replace that bra with a 1/2, 1/2. Now I have only diagonal elements. So I'm going to get a cosine T delta over 2. I'm going to get an I sine T delta over 2 times this big omega minus little omega over delta. I can take the modulus squared of that, and I'm going to get a cosine squared T delta over 2 plus a sine squared T delta over 2 times a big omega minus little omega over delta quantity squared. I can rewrite that cosine squared as 1 minus sine squared, and then I can recognize when I put everything over the same common denominator of 2 delta squared that I can rewrite that combination as gamma B1 over h bar delta quantity squared. And of course, if we add those two probabilities together, what we find is that the sum of those two probabilities is equal to 1. And of course, that's what it has to be even at all times, because the system is either in the upstate or it's in the downstate. So whenever I have that kind of either or, if I sum up all possibilities, I have to get 1. All right, we've now reached the end of lecture 2 of module 9, and this actually ends module 9. Module 9 was our shortest module in the class. We're going to be starting in the next class on module 10, and that class is going to be covering quantization of light, and it's going to help explain how the LIGO experiment works.